Hello, everyone. Today we are going to talk about one-to-one functions and their inverses. So we are going to start with definition of one-to-one function. A function f with domain z and range r is called one-to-one function if no elements of z have the same image f of x in r. Let me draw the picture. So here is my domain D. Here is my range R. And definition tells if we have two different elements in D, they are going to be converted in two different images in range R. So normally, function is allowing actually two different x's to be converted into same y. Remember quadratic function, for example, like x squared of -2 and 2 both equal to 4. So the normally function allows two different x's go to same y. Well, it's not going to be always the case, but for one-to-one function, if x's are different, y's must be different, and I'm going to write it down as a formula. If x1 is not equal to x2, then f of x1 is not equal to f of x2. So different x's go into different y's. Let me give you examples of one-to-one function and not one-to-one function. First, not one-to-one, so you understand what is actually the difference. Well, you probably recognize our standard parabola, right? That's x square function. That's why over here, x over here. Well, if I choose x1 somewhere here, it will go to this point and becomes this y. If I choose x2, which is like x1 but with minus over here, it will give me the very same y because, well, squaring is going to eliminate the minus, right? So this is not one-to-one. I'm going to also write down one-to-one as OTO. Okay, so function is not one-to-one. Which function is one-to-one? I'm going to write it down actually that f of -2, for example, is equal f of 2 and equals to the same number 4. So not one-to-one breaks actually the not equal sign over here. Now, typical one-to-one function is going to be a cubic parabola. So we have y over here, x over here, and the cubic parabola goes like this, right? So every x over here is going to produce a different y over here. So one x is going to produce one y. So you choose a different x, for example, that's x2, and x2 is going to produce a different y, y2. And they are not going to be equal if x's are not equal. Well, why do we need this? Well, we are planning to use one-to-one function to build an inverse function. Remember that, well, sometimes you can kind of Google your road to PCC from your house, right? That's, you enter the start point is your house and the end point is PCC, right? But if you go home, you go back from PCC to your house, and that's kind of inverse of what you had before, right? You are going to do same streets probably in just opposite order, like. So how it's going to work with one-to-one functions? So I'm going to write down over here, one-to-one. This one is one-to-one. How it's going to work with one-to-one functions? Well, if you allow your function with domain and range, bring two different values of x, x1 and x2, into one value of f of x over here. Then when you want to go home, your kind of Google is not going to know which of these two axes is your home. Should you go this direction or you should go this direction? So Google won't be able to find your road back. So to have an inverse function or to kind of go back, you will need to know exactly like one point which is connected to your like arrival place. And well, that's going to be your home. So this situation is not going to allow us to find actually inverse function. Inverse function is going to be labeled f inverse of x. So we are going to kind of drop this one and then we are going to have inverse. If all your direct values are having one image, then you easily can kind of say, okay, now if I start here, I'm going to arrive over here. And this way we are going to have f inverse for all these points in a range. Well, basically we define inverse for just like any one-to-one function. So if your function is one-to-one, then you can define inverse with domain, which is kind of range, and range, which is going to be domain. Let me kind of move over here and kind of write down if f of x with function f of x, sorry, function f of x with r, or with domain D and range r is 1-to-1, then exists inverse function f inverse of x with range. Oh, let's start with domain, with domain r and range D, which is defined as f inverse of y equals x, which is the same as f of x equals y. Okay, so if some x goes into y, then this y inverse function is going to take this y and bring it into x. Okay. Well, what are going to be kind of examples? We're going to start with example. Example number 1. For example, you know that function f of x is 1-to-1. And you also know that f of 2 equals 5. Question is, what is f inverse of 5? I'm going to draw the picture. You don't need to draw the picture every time. It's just like one time I'm going to show you how it works. So that's 2, and that's 5, and that's my direct function f, right? It takes 2 and brings it into 5. Now, what inverse function is supposed to do? Inverse function is supposed to take this 5 and bring it back into 2. That's going to be inverse function. So the answer to the question, what is inverse of 5, is actually 2, right? So you kind of switch range and domain and kind of independent and dependent variable. Now, another example is going to be the graph. Let me give you example 2, the graph. Imagine that we have a graph and the function is 1-to-1. You see that for every x, you have only one y. And the graph goes like 1, 2, 3. So here it equals 2, here it equals 2.5, and here it equals 3.5. And the question is, what is inverse function of 2? What is inverse function of 2.5? And what is inverse function of 3.5? Can we answer these questions looking at the graph? Well, you see that direct function takes 1 and brings it into 2, right? That's f of x. So what inverse function is going to do? Inverse function is going to take this 2 and bring it back into x. And well, what was x? X was equal to 1. Then inverse function will take 2.5 and bring it back into x, which is going to be 2, right? And 3.5, well, again, going back, that's going to be equal to 3. Okay, so that's how we use a graph, or we just can use a table. Basically, you just name your y's as your x's and your x's as your y's, and that's going to produce inverse function. Well, what interesting properties can have inverse function? Cancellation property. Of inverse function. What is cancellation property of inverse function? Well, first I'm going to introduce it as a graph, and then I'm going to write it down. So guys, you have range, the mean, and that was x, that was direct function f, and this is image f of x, right? So what inverse function is going to do? It's going to take this number and convert it into this x, right? F inverse. Well, if you start with x and first apply direct function, then take the result and apply inverse function, you are going to come back in x, right? That's kind of round trip. So I'm going to write it down. You take f of x, start with x, apply f of x, and then take the result and apply to this result inverse function over here. Well, you're supposed to go back to x, and that's cancellation property. You see that if you combine inverse function and direct function as a composition, you are going to get back your value of x. I'm going to write it down like composition form, but usually, guys, it's much easier to understand with parentheses. What is going to happen if we start actually with this point? Imagine that you start with this point, and first you apply inverse function. You apply inverse function and get to x, right? You go this direction. So you take f inverse of, well, I'm going to label this point as y, okay? Just to kind of have some letter. And then you go from x and use direct function on top of this. Well, you're supposed to go back to y again. And you see that, again, cancellation rule is working. You started at y and you are returning at y. You did a round trip. It does not matter how you do the round trip. Whether you start at home, go to PCC and return home, or you consider that you start at PCC, go home, stay there at night, and then go back to PCC. Still, round trip brings you to the same place. So the idea is that round trip always is going to bring you to the same place if your kind of trips are inverses. I'm going to write this as composition, but actually much easier to understand that as parentheses. Examples of composition. Example. So, for example, f direct function is a square. F inverse function. Well, what is inverse of a square? Square root, right? If you kind of well, square something like you square 2, get 4, right? How to get back 2 from 4? Well, you extract a square root. I'm going to write down one condition, that x greater or equals than 0, because we remember that totally x squared is not 1 to 1. But if you take half of x squared, like this one is 1 to 1, right? If you take the whole squaring function, x squared, that whole parabola, it's not going to be 1 to 1, but one branch is 1 to 1. If you write down x greater than 0, it's going to greater or equals than 0, is going to be 1 to 1. Okay. Now, how cancellation rule is going to work? Well, let me write the first part of cancellation rule, f inverse of f of x. Well, what is f inverse? That's a square root. I'm going to write down square root. Instead of x, I'm supposed to use my direct function, x squared. Well, we see that if you extract the square root of x, you're going to get x back. Well, normally it's going to be positive x, but because our x's are originally positive only, so that's going to be x again. Well, let's try to use the second part of the definition, f of f inverse of x. Now I'm going to write down f. F is my outer function and it's squaring, right? Inside, my argument instead of x is going to be a square root of x, f inverse. And I'm going to get, again, square root squared, which is going to give me x. You see, that's how cancellation rule is working. Okay, now, how to find inverse function? Well, let me write it down. How to find inverse function. Well, here, guys, we just guess that the inverse function of x squared is a square root, but how to do this like more mathematically? Let's see. Okay, we are going to consider an example which is going to describe the steps of how to find inverse function. So, example. Let's imagine that f of x equals 2x minus 1. This is just a straight line. I'm going to draw it somewhere here. 2x minus 1, something like this, a straight line. Not exact graph, but just approximately how it's going to look. You see that it's 1 to 1, so it's going to have an inverse. Well, what we are going to do, the steps to find inverse. They're asking, the question is, what is f inverse? Step number 1, write down your function in terms of x and y. So y equals 2x minus 1. Step number 2, switch x and y, because to find inverse, we will need to exchange x and y, right? Put y instead of x and x instead of y, because y's are going to become independent variable, our argument, and x's are going to become dependent. So switch means that just instead of y everywhere put x, instead of x everywhere put y. Step number 3, solve for y. Solve for y means that just find y on the one side of your equal sign and everything else on another side. How do we solve for y? Well, let's write it down. X equals 2y minus 1, right? I'm going to add 1 on both sides and write down x plus 1 here and 2y here, and then divide by 2, and I'm going to have actually x plus 1 over 2, over 2 equals to y. Last step is just to write down inverse. That's going to be your y, so that is our inverse. F inverse of x is going to be x plus 1 over 2. Sorry, my computer likes to fix stuff for me. Okay, that's how they define inverses. You can always check your inverse if it like cancellation rule is going to work. Normally, guys, if I need this, I'm going to ask about this. But if you are interested, you can do it on yourself. So I'm going to check just one part of cancellation rule. Normally, cancellation rule is supposed to work both ways, but I'm going to check just one part. That f inverse of f of x equals to x. Is it? Well, let's check it. So f inverse is x plus 1 over 2. Now, instead of x, I'm supposed to use direct function. What is my direct function? Direct function was, let me go back, 2x plus 1, right? It's over here, 2x plus 1. So I'm going to put it here, 2x plus 1. Or minus 1, so need to erase again. Minus 1. 2x minus 1. I'm going to simplify this expression. 1 and 1 cancel, 2 and 2 cancel, and I just have x. You see that cancellation rule is working. Okay. Now, let me go back to the graph of inverse function, because I want to talk a little bit about graphing, but I want to go first to the picture. You see, guys, all functions which are one-to-one have a same property when they are graphed. If you draw a horizontal line through your graph, let me go to the first graph over here. If you draw a horizontal line through your graph, horizontal line must intersect your graph only once. Well, just look over here. If it intersects your graph twice, like over here, means that for two different axes where it intersects the graph, they're going to be same y. It's not one-to-one. So this is called horizontal line test. Horizontal line test. So if somebody gives you a graph and they're asking, is it like one-to-one or not? You just draw horizontal line test, imagine it, and check if for all horizontal line tests, it's going to intersect your graph only once, like over here. Then it's one-to-one. Also, what we are normally doing when we graph inverse function, remember that f of x equals to y, right? For inverse function, we will kind of have another statement which is going to say that f inverse of y equals to x. On my graph, this one is going to look like a point x, y, right, on my graph. So I'm going to make it like somewhere here x and somewhere here y. The point is x, y. For inverse function, x is going to be like my y, right? And y is going to be like my x. So kind of points are going to switch. And I'll just need to mark on my, let me make it orange, on my x-axis now y. Well, I'm just going to measure it like about 4 squares, 1, 2, 3, 4. Somewhere here is going to be my y. And my x is going to be instead of y, about 2 squares, somewhere here. And the intersection of these 2 points is going to produce my inverse point. This point is going to be inverse. What is interesting, guys, if I draw a bisector of the first quadrant, these 2 points are going to be symmetrical about this bisector. Symmetrical means that they're going to be on the same distance from this line, same distance, and this perpendicular line between the points. This is going to help us to actually graph inverse function if somebody gives us direct one. Let me kind of go to the free space on my whiteboard and kind of describe it. So I'm going to write, oh, sorry. Allow me to erase, I want to use black marker. So I'm going to write down that if point P has coordinates x and y and it's produced by equation f of x equals y, and point Q, which is kind of symmetrical with coordinates y and x, is going to be produced by f of y equals x. Now, imagine that, well, I have some curve for direct function. This is my x square. You see, these points are kind of my direct function f, right? Now, what is going to happen if I switch the coordinates? For example, this point, coordinates 1, 1. If I switch them, well, I'm going to get the very same point, right? The coordinates are going to be still 1, 1. So my inverse function, I'm going to use a red color for inverse, is going to be the same point. How about 0, 0 point? Well, if you switch 0, 0, it's still 0, 0. How about this point, which is 2 and 4? Well, the coordinates are 2 and 4. For inverse function, the coordinates must be 4 and 2, right? So I'm going to choose 4 here and 2 here, and that's going to be the point of inverse function, right? Now what I'm going to do, I'm going to just connect these 3 points. We already know that inverse is a square root, but graphically it's going to look like this. And if your function is not as simple as quadratic function, you will need to draw a bisector here. Bisector, it's something which divides this 90 degrees angle into 45 degrees angles. And the points are of inverse and direct function are going to be kind of symmetrical. Well, my picture is not super good, but I'm trying to show that we are reflecting actually direct function over this line. Like imagine that you have a mirror here, and that's going to give us inverse. Okay. Now, what else? Well, I want to go over like some self problems. So I'm going to write them down. And again, the rule is same. You solve some self problems on your own and kind of then watch my video. For the first problem, find f inverse. Problem number 2, a little bit more complicated. X over x plus 2, same, f inverse is a question. Problem number 3. Well, I'm giving you different problems for finding inverse, so you practice a little bit with different arithmetic operations, some algebraic operations as square root, to find inverse. And the last one is graph inverse. I'm going to give you 2 graphs, and on each graph, I want you to graph inverse function. That's my first graph. I want inverse here. I'm going to label it A, and somewhere here is going to be my second graph. For the graphs, I just want to see the graph of inverse. Okay, I'm going to count to 5 and wait until you kind of solve it and go back and check your solution. Okay, so 1, 2, 3, 4, 5. I'm going to continue solving it, but I suggest you to try on your own. So guys, I'm going to solve the problems over here. Okay, solutions. Let's start with the first problem. So remember, I was telling you step number 1 is to set y equals the function 3x cubed plus 8. Step number 2, exchange x and y. So I'm going to have x equals 3y cubed plus 8. And step number 3 is to solve for y. So I'm going to, well, maybe I'm going to just solve it over here as step 3, but I don't want to rewrite everything. So I'm going to subtract 8 here and have x minus 8 equals 3y cubed. And I'll need to divide by 3 both sides, right? So I'm going to have x minus 8 over 3 equals y cubed. And the last step to find y is to extract the cubic root. Now, that's going to be my y, right? And the final answer is going to be f inverse of x equals a cubic root of x minus 8 over 3. Sorry. Okay, so that's the first problem. Well, I'm not going to fit second problem over here, so I'll go like down, okay? So problem number 2, f of x equals x over x plus 2. Well, step number 1, y equals x over x plus 2. Step number 2, x equals y over y plus 2. And now I'll need to solve for y. Here, it's going to be a little bit more complicated because I'll need to actually, well, deal with a fraction. Step number 1 for fraction is to bring it to common denominator. So here is y plus 2 missing, right? I'm going to multiply by y plus 2 both sides. Getting this. Step number 2 is to open parentheses. Y x plus 2x equals y. Step number 3, because we are solving for y, we will need to isolate y on one side. Well, I'm thinking that I'm going to move this one over here and write down that y minus yx. 2x, I'm going to take y outside of parentheses. And then kind of what next step to isolate y is to divide by 1 minus x. So it's 2x, 1 minus x equals y. And that's going to be my inverse. Okay, so that's my inverse. Sometimes, guys, inverses are going to have restrictions on domains, but they usually are the same as restrictions on a range from direct function, right? Because we remember that domain is becoming range and range is becoming domain. The next problem is a square root problem. So problem 3, we have a f of x equals 2 plus square root of x plus 1. So again, step 1, y equals 2 plus square root of x plus 1. Step number 2, x equals 2 plus square root of y plus 1, exchanging x and y, right? And step number 3, we are solving now for y. So I'm going to subtract 2 from both sides, minus 2 here, minus 2 here. I don't want to copy everything because of one step. And to kind of find y, we'll need to clear it from the square root. So what I'm going to do, I'm going to square both sides. Here, the square is going to stay. Oh, sorry, there was minus. Sometimes when I copy something, I change minus to plus. Please watch like my work. Here we are going to have y plus 1. And the last step is to subtract 1 from both sides. So x minus 2 squared minus 1 equals y. And that's going to be my f inverse. X minus 2 squared minus 1. Okay. So we solved first 3 problems. For problems, maybe I should keep a little bit longer it on board. For a last problem, problem 4, we're just going to graph inverses. So how I'm going to do this? Well, I'm going to draw a bisector of the first and the already, sorry. So that it's line y equals x. And now I'm just going to imagine reflection of the points. For example, this point will be reflected into here, right? This part of the curve, which is approaching x-axis, is going to, on this side, when I reflect it, approach y-axis. And this part will go like this. And that's going to be f inverse. Actually, direct function is exponential function. It can be something like 2 to the power of x, and the inverse function is actually log with base 2 of x. You don't need to know exponential log functions. We are going to cover them in like maybe a couple of months, but that's just how to find inverses. For the next function, I'm going to also graph y equals x line and try to find inverse points. First, 0 point is not going to move, right? 1 point is not going to move, and negative 1 point is not going to move. The part which is above the curve is going to be now below the curve. Here, there's supposed to be black part above, below, and that's going to be above now. And this part is going to curve like that. This part is going to curve like this. It's like a reflection. My pictures are not super good, but that's a final answer. Okay, that's all for today's lecture, and please do your homework. Okay, I'll see you next lecture.